I'm Thomas. I'm a freshman mechanical engineer.
I'm Joey, junior electrical engineer.
I'm Eamon. I'm a senior music major.
And I'm Jeremy. I'm a computer science and biology.
And this is the Dubsteps 2.0.
We're trying to map the gestures that you're doing with your feet to some sort of musical expression that makes sense to it.
So you can play it seated, and this is kind of the drum module of that mode, which lets you play various drum sounds with the buttons in the shoes. The other part of this seated mode is there are IR sensors on the inside of the shoe that measure the width between the shoes. And so using that, we can control the pitch of the instrument. And then
So you are stepping through a pre-programmed sequence of notes.
Yes.
So you've got a total of 22 inputs into the Arduino. The first 4 are coming from these buttons on, there's one on the heel, and there's also one on the toe, which you can't see. So whenever you step, it triggers those buttons. That's just a binary input, which means it's just yes, no, off, on. Then underneath, we have this spring setup. Originally, we had FSRs triggering node on, node off, but the problem with that is that the FSRs are very sensitive. So now the FSR is only triggered when you take a significant step, which is the point of the springs. And as a result, now we can use the FSRs for something called aftertouch, which is like after you trigger the note, it can then affect a different parameter of sound. So the FSRs are responsible for aftertouch. There's one on the forefoot, one on the heel. We have accelerometers, one on each foot. You can barely see it, but it's that little black dot. And that has acceleration in the Z, X, and Y directions. We mostly focused on the Z direction except for the drumming mode, because the X direction gives you the tambourine. Yeah, so that's another set of inputs. You have the flex sensor right here, which you can't really see, but it's outlined in green. And the more you flex, the more different the reading is, and then that's another input for the sound. And IRs. So we have one IR set up on the right shoe, and that's giving you width between the two shoes, and each shoe also has a height IR pointing straight down, so that's telling you that height from the ground.
Each sensor can be mapped to a different gesture. So this module, our IRs are matched to the pitch for each note.
there's the note ons, which are controlled by actual buttons that are mounted in the soles of the shoes. There's buttons in the toe and heel of each shoe. But they don't all correspond to node ons in each patch.
When he presses it harder, something will change in the module.
So that's controlling the oscillator frequency, the oscillator octave of one of the parts of the patch.
So we can bring in higher notes as we press down on the heel of the foot that we're playing the notes with.
On the back there's here, turn around, give him a twirl. Yeah, so there's a 3D printed box which contains the Arduino and a proto board that has all the connections from the sensors.
We were trying to make this wireless, so we wouldn't have to have this cable. Proved very difficult. We're getting communication between both computers, but then when we tried to use it into what we used, which was called Max, which is processing all the data, it's giving us a lot of issues.
So we're standardizing all of our sensors to the same value range. What that means is we can use all of them as analogs for each other. So if we want to map any of these to any sort of control, we know they're going to have a certain range of values, so we can assume that that control mapping works. We have all these outputs, and we've labeled all of these here so that we can now map easily just one of these outputs to anything we want down here. So in the case of the drum patch, where we're just triggering a certain note with each toe or each button, right? It's as simple as having a little tiny module which says send this number to the drum module, and whenever I press this button. So in this case, we have this little patch here, which what it's doing is giving you the chance to select what octave you're looking at. So in this case, we've restricted to a major scale. It's choosing what major scale you're looking at. So you can use this top keyboard to select which one you want. You can switch octaves using either of these buttons. You can also alternatively actually map an input from the shoe to the switching of those octaves. So if you wanted to have, for example, the ability to change the note and then change what octave you want with the toe and button on that other foot, you could theoretically do that. And it'll also display to you what note you're on, so you can give a sense for actually what you're playing at the time. Any of these modules, all of these are labeled so that anyone wanted to make their own patch, they can just hook them up however they want them, and it'll work. And it actually makes programming with this really easy.
So you designed this to be as flexible as possible.
Exactly. There's a piece in the background which is tracking what part of a step you're doing and defining what possible expression is given based on which way you're going. So for example, if you're moving forward through your foot versus like forward through a step versus walking backwards, there's a difference in what the output is.
So you're remembering the order of the sensor pulses that are coming
Correct.
in and making logical decisions based on that.
Correct.
Also, you could walk backwards through a sequence of notes instead of forwards, which would be really cool.
Fun.
Or you could use it as like a sampler. It's playing a sample. You go forward through the sample. You go backward through the sample, which could be pretty cool.
Yeah.
And what happens if you moonwalk?
Michael Jackson plays.